Hello, my name is Josh Cahill. I am a lunar geologist and remote sensing scientist in the Moon and Rocky Body section at the Johns Hopkins Applied Physics Laboratory. I'm also the Lunar Technology and Science Integrator for the APL Lunar Surface Innovation Initiative for NASA. Let's talk now about the lunar surface terrain. The wide variety of lunar terrains and geologic structures of the Moon can be seen in this slide. Most evident is the presence of two chemically distinct terrains, which are visibly distinguishable. The mare are the dark regions containing greater concentrations of iron oxide and titanium oxide, and have higher calcium oxide to aluminum oxide ratios than do rocks from the highland areas, which are the brighter regions. Physically, the topography of the highlands are rough and intensely cratered, while the mare topography is relatively smooth. Interestingly, the mare basalts cover about 16% of the lunar surface, with 93% of the mare located on the lunar near side. Therefore, mare basalts cover about 30% of the lunar near side, but only about 2% of the far side. This imbalance is suspected to be due to either the absence of deep mantle melting beneath the lunar far side, or the impotence of rising basaltic melt due to a detectably thickened anorthositic crust. This is one of the great mysteries of the Moon, and looking at the samples returned from the Moon can help provide clues with which we can piece together a better understanding of the Moon's internal structure and history of crustal emplacement. More than 3 billion years ago, it appears the igneous activity on the Moon was relatively sparse. As such, the complex topography of the Moon has been largely controlled by sporadic asteroid impact events, resulting in a high population of craters spanning the Moon's surface. Craters occur in all shapes and sizes, and small meter-scale craters are the most abundant. Craters can be classified as simple, which are characterized as bowl-shaped and rounded, or small with flat floors. With increasing size, craters can be classified as complex, consisting of larger diameter flat floors with terraced and crenulated rims, slumps, uplifted central peaks, or a combination of these. Craters larger than 100 kilometers and characterized with a ring of peaks are called peak ring basins, or just basins. One of these is South Pole Aitken Basin, one of the largest known impact features in the solar system, located on the far side of the Moon. Not only the topography, but the composition of this basin appears to distinguish this region from the other highland regions. The depth of many parts of this basin, the materials further excavated by subsequent cratering after basin formation, and its anomalous geochemical signature make South Pole Aitken Basin an important location for a sample return mission. Mare surfaces are cut by deep channels called rills, along with faults that buckle the same surfaces. Mare surfaces also have domes, which are broad, convex, and circular landforms with unknown formation mechanisms, but are largely attributed to the eruption of lavas. Another important geologic feature on the Moon are pits, such as the one shown here within Mare Tranquillitatis. Pits are found in either mare basalts or in impact melt regions and are characterized by near vertical walls, inward sloping rims, and rocky floors, and are hypothesized to be formed by the collapse into pre-existing subsurface voids. The unique morphology of the lunar surface poses a plethora of challenges to systems and operations. Most evident, terrains exist that can make it difficult to land safely, move around, and communicate with the nearby systems or Earth stations. Recall the 6 Apollo landing missions. All of these faced potentially mission-ending hazards, summarized in the table on the right. These hazards were in the form of large boulders, craters, and slopes that were perilously close to the landing site. As documented in the paper, The Challenge of the Safe Lunar Landing, Apollo 11 had to adjust its downrange and cross-range positions during descent to avoid landing on a field populated with boulders and surrounding a large, sharp-rimmed crater. Similarly, the Apollo 15 mission landing site was near the foot of the Apennine Mountains next to the Hadley Rill. After its spacecraft pitched over, the crew was only able to recognize the rill, and the terrain was different than what they had trained for. Immediately, they tried to identify another recognizable feature and noted the south cluster terrain. They performed several landing point redesignations, moving uprange and avoiding craters. When low enough, they switched to manual control, and Colonel David R. Scott headed for a reasonably smooth area and landed as best as he could manage. The landing was successful, but one of the rear pads did end up in a crater. Colonel Scott mentioned that at 50 to 60 feet, the total view outside was obscured by dust. This is an important consideration, as dust will not only compromise vision, but can affect sensors that will inform the crew regarding altitude and translational velocities over the ground. Rover navigation technologies will encounter local slopes and uneven objects like steps, boulders, and craters. A lot of these features cannot be known beforehand, and some may not be negotiable. As such, mobile assets will need to prepare for these terrains to avoid hang-up, tip over, slipping, and sinkage in the loose regolith. Another important challenge is communications. The communication and navigation infrastructure needed to support the future lunar missions demands modular lunar surface communication terminals that are flexible for use in stationary, integrated, and mobile environments. Locations for these terminals and mobile asset paths must be chosen to avoid the occurrence of blockage and frequency range limitations due to the local lunar surface topography. And at the poles, local terrain will also often affect illumination and direct Earth communications in predictable but significant ways on variable timescales. Surface mobility will be crucial for accomplishing many tasks, ranging from site preparation, construction, and local transportation. To safely and efficiently explore the Moon's surface, design solutions must be implemented that will overcome target terrain and regolith challenges. Consider the use of a system for all-terrain endurance, such as the Apollo roving vehicles. The rover wheels consisted of a spun aluminum hub and wide tires made of woven steel strands. Titanium chevrons covered 50% of the contact area to provide traction, and each wheel had its own electric drive, a DC series wound motor capable of 10,000 revolutions per minute, attached to an 80-to-1 harmonic drive. This remarkable machine, as the crew termed it, proved to be reliable, safe, and flexible, able to traverse very rugged areas. Other successful lunar rovers include the Lunicod rovers, that had 8 wheels, each with independent suspension, motor, and brakes. Another example of a successful planetary rover is the Mars Pathfinder rover. The rover wheels were made of aluminum with stainless steel cleats for traction. But what was most unique was the rover's rocker bogie suspension system, which did not use springs. Instead, joints rotated and conformed to the contour of the ground, providing the greatest degree of stability for traversing rocky and uneven surfaces. For any future design, it will prove crucial to carefully select the rover wheel materials and evaluate them in a regolith simulant testbed with simulated topographies and a setup that can mimic partial gravity. In addition to mechanical features, future guidance, navigation, and control systems will also be instrumental to successful vehicles and will need to have onboard capabilities that combine sensing and computing. For example, terrain relative navigation for landing will make use of onboard camera images and range sensor data of the surface to localize the spacecraft with respect to the reference map generated ahead of time. Similarly, optical and tactical sensors on a rover will make references to characteristic terrain features to estimate local position and inform translational movement. These capabilities are envisioned for better hazard avoidance and precision navigation and will enable future autonomous systems. Thank you for watching, and I hope this module has been informative.